so that we are losing the both of your life.
Is this your normal slot or similars?
Yes, yes.
Okay.
And no, I mean, depends on the the room can be filled easily, but for the very big, still something else.
Yeah, that's more important. The PhD students.
I think I need it. Okay, so that's it. Now you are live and you can go on to Zoom and forget about YouTube until sometimes in the morning want to make sure that it's done. Or wait, so.
I think I have a few friends watching online, so that's also. Oh wow, okay. The virtual room is boosting.
We'll start the seminar in a couple of minutes. It's very late because we have 70 people.
It's good. It's like get people. I have a little
I really is accessible if you prefer to move and grab it.
Yeah.
For Zoom, you need to be the sorry.
Yeah, for Zoom, they need to hear me first. I'll shout very loudly. It's good. It's like the old times. A good get keep with 5 people showing up.
Okay.
Hola. Buenas.
So we start. Hi everyone. So it's a pleasure for me to introduce Nicholas Jannsen. We invited him to visit us from La Palma. He's a new staff astronomer at the ING. INT?
ING. Yeah. Groups of
at the ING. And he's also part-time postdoc at KU Leuven in Belgium. He's working on Plato, improving performance and doing simulations. And he's going to tell us today about what we can do if we explore the faintest limit. He started as a stellar astronomer for his PhD. So he has moved through what Plato can do between the PhD and the postdoc. So let's hear what he has to tell us. Thank you, Nick.
Okay. Thanks, Anna. Okay, well, thanks for letting me come here to ISC and introduce my recent work, among many other things I'm also doing at the moment. But as Anna said, I work at the ING right now as a staff astronomer, and then still battling between work-life balance with 2 different jobs. So I hope you will enjoy the little view into Plato's view on supermassive black hole binaries. Okay, so to start with, I also want to say, if this one wants to react. Okay. I think it's because it needs to be pressed one more time. But I just wanted to say that I will use this acronym quite a lot. So supermassive black hole binary. So I just condensed it because it's quite a mouthful. And this work is in collaboration with a few people here that I have been working tightly with. So I just want to highlight that. And my work is, as also Anna said, that is correlated to my work at Leuven, which unfortunately I'm not a postdoc there anymore, but I was just until the new year, basically. So let's dive into the research of supermassive black hole binaries, or in general, just supermassive black holes. Why do we care about them in the first place? Okay, get messages on my screen. So I will say there's quite a lot of cool things that we can do with them and a lot of things we can learn about the universe. And of course, some of the most energetic phenomena in the universe is coming from the accretion flows of supermassive black holes, usually centered in the galaxies or the host galaxy. We can also learn quite a lot about fundamental astrophysics, or physics in general, I say, about space-time itself if we observe these phenomena. And we, of course, know that galaxies, they kind of have a co-evolution with their central supermassive black hole binaries. For example, the correlations between the balls, the size of the balls and the mass of the supermassive black hole is one correlation, but you have many others as well. And I think what's really exciting about this field is that we're starting to kind of uncover and see new science that we couldn't do before, because we have like extremely good telescopes and extremely advanced instrumental techniques that we can employ now. And some of the things we have, for example, been doing, or I say we, but some the very, very technical astrophysicists around the world has gathered like data for a full Earth-side telescope that you can use to image, for example, these supermassive black holes in other galaxies, for example, the M87, and in our own galaxy, Sagittarius A star. And what I find really interesting now is that if we move beyond just one single supermassive black hole to a binary system, we are now starting to see the evidence that there might be a gravitational wave background in the spectrum from this nanohertz gravitational wave signals that we can deduce from, for example, pulsar timing arrays. So these are like internal clocks in our local galaxy that we can use to kind of see the bending of space-time itself, and then discover that there might be some of these supermassive black hole binaries that merge together over the course of many years. Okay, so with a little bit of motivation, we can then go to, for example, understanding how do these supermassive black holes form in the first place. So now we only think about the single black holes. So of course, the hierarchical galaxy formation that we usually learn in our undergraduate school of astrophysics is that we have some smaller galaxies, primordial black hole will form, and then depending on how these galaxies then aggregate matter, there will be bigger ones, there will be smaller ones, and we can either get like a bit more active galaxies where we have a lot of matter close to the center of the galaxies. So there's a lot of accretion, for example, that could be involved in these kind of objects. Or we can have more like, say, I would not say normal, but like spiral galaxies that are slightly different in their activity. And if we just fast forward, we then have a galaxy that's sort of built up where we have either a spiral structure, could be over many, many courses of collisions. We can also have elliptical galaxies. But the whole point is that we, at the end of the day, will come out with a black hole in the center of a galaxy. And depending on how many collisions there have been, we will then get bigger and bigger black holes. Okay, so the evolution of then, if we take the binary system, is that we have this kind of like old school view of how these supermassive black hole binaries are formed. And they are really simple in the sense that we can think about the same formation process they have for the single supermassive black holes. So we basically have galaxies colliding together, but in this case, we have like really, really massive galaxies colliding together. And of course, this happens throughout the universe, but probably not all the way to early times. So in very, very high redshifts, these things were not really seen if we go very, very far back. But as we go into the main prime area of like galaxy formation, we really see like a lot of these candidates for supermassive black hole binaries. At least some of them we see as these dual AGNs. So basically two galaxies that are both active. And the activity we usually assign to a supermassive black hole accretion. Okay, so that's the sort of the formation when we have like two galaxies colliding together. They will slowly start to be bound, and then the cores of these galaxies can then merge together. So that's the kiloparsec distance formation. Then the question is what actually happens in the stage between when we have like this kind of sub-parsec evolution of supermassive black hole binaries. And of course, we know, because we have already observed some of these, that when we bring two supermassive black holes or any black hole paired together, a neutron star massive object together, we have an inspiring of gravitational waves just because they radiate gravitational waves, and they will then coalesce in a merger at the end here, at the very last stage here. But the question is, what happens in between these two stages? And I think nowadays it's not really, as we can state it here, probably some of you know this as the last parsec problem. I would not say that this is really a problem, but what this problem was stating in the first place, that how do we go from the formation of these two supermassive black holes, bound them together, and then if they get gravitational bound and there's nothing else interacting in the system, how do they then go from that scale all the way down to merger within a Hubble timescale, so within the timescale of the universe? And of course, I think this is not really maybe stated as a problem anymore, because we have many hydrodynamical simulations that shows that there are different scenarios, the way to get there from phase 1 to phase 3. And so I think this like the middle scenario here, the step 2, is quite an important step to understand how is the demographics of these supermassive black hole binaries, and what is the physics that we can understand from them and learn from them. Yes. But besides, of course, that we have this scenario of the evolution of supermassive black hole binaries, we also want to go out and see if we can find them. And as I already alluded to, is that massive black holes, they typically form an accretion disk, and this is some of the very, very high energy phenomena that you see in the universe. And I will just give you an example here of like a very, very beautiful radio galaxy that has two like big radio lobes. And this forms into the general overall scheme of how we think about active galactic nuclei, so AGNs. And what you see is basically, if we take a zoom in on such a system, typically if we just have a single massive black hole, we can see that it forms like a torus with some accretion flows, and we have kind of different broad line and narrow line regions where we can see different radiation. And I think this is interesting because if we imagine we have these signals, of course, we now get a direct signature of the black hole from photometric observations, so in electromagnetic signature of the object. Okay, so but if you had two of these, of course, the accretion flow can then also disclose that we might have binarity, and that's a very interesting thing that I will show you a bit more today. Okay, so the schematic you see here, I should not go too far away. The schematic you see here is basically a galaxy's projection of all the supermassive black hole binaries that we have sort of seen in literature to date. And I say candidates here in quotation marks because most of these black points you see around the sky here from different studies have actually been more or less disproven to date. And the reason is because, as I said, when you have these accretion flows, you get a very, very stochastic signal that comes from the accretion flow onto the black hole. And that can be easily confused with other signals that we usually link to binarity. And I will show you some of the things that we are looking for. But essentially, most of the black holes binaries we have found today, they are probably false positives. I have highlighted three small dots here, which are still surviving candidates, and especially this little candidate here, which we call spiky, which falls within one of these regions that you can see. I will go into more detail, but this is essentially the field of view of the upcoming Plato mission that I will kind of focus on today. So it's nicely located within the northern field here, and therefore it might be an interesting target to kind of follow up with our very high precision space-based photometry. Okay, so how can we circumvent this situation from having almost no supermassive black hole binaries or even any candidates to actually go and get like some kind of a demographic of like this, how these systems look like in the end by discovering them? One thing I think is very interesting is that we can start to look into, of course, beyond the accretion flows that they have, but we have to use them to actually utilize some of the signatures that they give of binarity. And one of these signatures could be, for example, gravitational self-lensing. So what you see in this video is that when you have two massive black holes that have an accretion disk, is that you get a relativistic effect where you have the bending of the light throughout this massive potential of these black holes, which kind of both amplifies the signal in these specific locations where you have like an eclipse. And these signatures are very sharp, and they happen very specific in phases of the orbital configuration. So they are kind of like pinpointing, saying down where, if you find them in certain configuration where we know there is sort of a binary signature of maybe a sinusoidal signal due to Doppler boosting. So we have these beautiful light curves that looks a little bit like radial velocity light curves. So in specific phases, we can get exactly a peak. And I would say is pretty good smoking gun to say that we have some indication that this might be a supermassive black hole binary. But of course, the issue again, as we will come back to later, is that these very sharp features that give rise to or comes from gravitational self-lessing, they can also be confused quite easily with, for example, a damped random walk that you have from AGN variability. And so my motivation today is actually starting from a paper that was submitted quite some time ago. There was a Kepler observation of the object spiky. And this is probably the best case scenario we have so far of a supermassive black hole binary, where we both see this beautiful sinusoidal signal, or a little bit stretched sinusoidal signal, which is the Doppler boosting. So that's essentially also another relativistic effect that comes from the boosting of the light as the objects are moving around each other. So in this case, we basically are assuming with this light curve that there is a massive black hole that is lensing and also boosting the accretion disk of a smaller black hole that is orbiting this system. And so you can see what I just talked about is that a specific phase is exactly when we have the object lensed from the background. So this is a small black hole. We get this beautiful spike. So this is one of the things that we wanted to investigate. So could we actually observe this with Plato? So remember, we have a spaciometer that's quite different. Kepler was observing quite faint, whereas Plato will be observing much brighter objects. So this is really pushing it to the faintest limit, as I already alluded to before. Yeah, and this is just to highlight again that these signatures here are probably more probable to search for, although they are also difficult to find, of course, because we have to have the right conditions in the orbital configuration before we will even see lensing. For example, you need to have an inclination that is relatively close to 90 degrees if you define the system to be edge on at that stage. But I think this is very interesting. So the question is there any hope for us to go from a light curve like this, where you have all of this variability from the AGN itself, so the accretion flow onto the black holes, and can we disentangle this from the real model fit here we have from, for example, Spiky, that was published by Hu et al. Okay, but I think if we talk about Plato in the future, one telescope I must mention, is that we might enter a quite big revolution in terms of data, because we just have a new telescope online, which is the Vera Rubin's telescope with the legacy survey of space and time, which is like a huge survey that will basically cover the entire southern skies, because this is located in Chile on its own little mountain top. But the advantages of this survey is that it has a huge digital imager. And this is just the focal plane of you see here on the right compared to the moon. And so essentially we will, every few nights or every week, we will more or less get a new data point, image of the same sky. And this is a survey that will continue at least for 10 years. So we have the potential to really monitor a lot of AGNs to search for these binary signals in the relativistic signatures that they have. So I think this is quite an exciting time. And so, of course, we can always ask the question then, if we have this beautiful survey, why do we need Plato in the end? And so what can Plato offer to this era that we have now with LSST just being online? You've probably already seen this beautiful picture here on the right, where you have like thousands of galaxies just in one single snapshot. And this is not even close to being the full field of view. This is just a very, very small field of view of LSST in one single image, or maybe multiple images here it has taken. So, and to answer that question, I, of course, would like to also introduce Plato. So what is the Plato mission? How does it look like? So on the left here, you see the spacecraft design. So Plato is a future space photometer, which has basically 26 cameras. The two in the top are for guiding mainly, but you can also use them for very bright stars. So that's a complete different project compared to what we are talking about today. But the main instruments on Plato is these 4 groups here of 6 cameras, which together basically are spread out a little bit from an angle from the bore side of the spacecraft. So what you're seeing is essentially like a larger field of view, which I can show here. So you get this, what I will usually call a visibility flower, where you have the pointing of the telescopes, or the 4 groups of telescopes. They're giving in these different colors here, red, blue, yellow, and green. And then you can see the overlap of the cameras. So in the center of the field of view, you have more visibility. So you have 24 cameras, and then you have 18, 12, and 6 cameras. So of course, the noise level sensitivity you're getting, it depends really where your targets are located. So this is quite important for the future observations. And the strategy that we have for Plato is the following, that we want to observe at least 2 fields for 2 years. Of course, this strategy can be changed in time. We don't really know if this is actually going to happen, but what we do know is that we will have first a southern field here, which covers the large magnetic cloud. So it's pretty cool for a lot of scientists, I think, studying extragalactic studies, whatever. Or you also have the northern field here, which is overlapping with the Kepler field. And that's why it's important, because remember, it was Kepler that discovered, or at least observed, this supermassive black hole binary spiky. So that's why it's quite cool that we might be able, in the future, after 2 years into the mission, we might be able to then also get some data of this little object. Okay, but as I said, these 2 fields and the strategy is driven by the core science of the space mission. So of course, Plato is going to be looking for exoplanets, actually transiting exoplanets. And in the spirit of the new movie we have about the Pandora moon and Avatar, I put like a little binary, a little exo-moon planet system here for fun. But essentially, we have a very, very high cadence with Plato because we want to be able to really, really track and monitor these exoplanet transits. And this is actually excellent news, because with that, we can really, really start to study the short period variability we also have for any other phenomena in the universe. And Plato will give you data products that are in 2 different shapes. We can either have onboard photometry. So this is just a simple aperture photometry method, where we just extract what is optimally available, lowering the signal to noise, trying to avoid as many contaminating stars. But of course, that method is only good to a certain level. So for some of the core science targets, we will also be extracting what we call PSF photometry, and we save the pixel data. But since Plato has like a huge field of view of more to 2,000 square degrees of the sky, we are not able to download all the data, unfortunately. It would have been really awesome to have full frame images of everything we see, but it's just not possible. So therefore, we had to kind of go with an intermediate step where we either get some of the images, we call them 6x6 pixel files, or we get the onboard data here. And for our purpose, we don't really need this. We can go for the lowest data product, which will help us a lot in the future, because we have to fight for the same time, which I also will come to later in this talk. So exactly in the name of the Plato Comprehensive Science Program, you can be a guest observer and you can apply for time through these different packages that we have here. And all of them are kind of working on different aspects. For example, as Anna already said, I actually been working in the pulsating stars working group, mainly throughout my PhD, and then slowly transiting into this transient phenomena, extragalactic science, and now focusing a little bit more on supermassive black holes and their binary systems. But this is just to let you know that we have 8% of the telemetry is actually offered to the community, including all of you. And so you can apply for it with a deadline now in April for the first year of the data in the southern field. So this is coming very soon, and that's hopefully very exciting for a lot of people. Okay, so I would say, just to give you a little introduction, without any showing any science so far, what can Plato offer to LST in this era of LST? And I would say we have extremely high cadence space-based photometry, uninterrupted for 2 years. And that might really help the case of having a follow-up studies compared to what LST is going to be looking at. So I think this is quite important, and we can use this, and we should use this and utilize it for AGN research. And then we also can use it to expand it as this observable sky. But remember, we are limited with that survey mainly to the southern sky. So we can actually use it to expand it a bit and get more knowledge about the northern sky as much as possible. Okay, to get to the point where we actually can start analyzing some of these say simulations and also like getting into the instrumentation of how Plato will be observing AGNs in the very faint limit, we kind of need to understand the instrument itself and how we would simulate it. And that's been kind of the core point of my entire PhD, to understand the instrumentation of Plato. So that's my main expertise, I would say. And just to give you some motivation why I think it's very important is that, of course, working together with people, some of these people you see in the picture here on the left, you have the preparation of the mission where you are literally assembling the telescopes. So in that kind of sense, you can really use simulations for the preparation, the commissioning, also how to design it in the early stages. And throughout my PhD, has been helping to test kind of data structures streaming through the pipelines of Plato. Another thing I also think is important, of course, I think we should never forget is that compared to Hubble, we cannot do service missions to Plato. It's going to be sent so far away that we will never see it again. So it's better make it correct in the first place. Yeah. Okay, we don't have as many single point failures as James Webb, but it's still important, I'll say. So what is actually the thing that we are modeling when we do simulations with Plato? So we have a simulator that is called Plato Sim, which has been the main tool of my PhD and for my work in this seminar as well. And what we do is that we simulate a single camera, essentially. So we have a full camera shown here for Plato on the left, which is end-to-end the optics, all the way through down to the focal plane, where you have CCDs, readout electronics, everything. And so all these components are modeled in our simulator, and we therefore also produce pixel-based simulations. So that's what you see here on the right-hand side. This is just a little preview of a smaller subfield, but remember the focal plane of Plato is actually quite big. It's 4 CCDs for every single camera. So you have around something like 104 CCDs or something in total in the whole focal plane of the payload. And if you zoom in again, the simulation we usually do, and I usually do to save some time, is that we will only get data from 6x6 pixels, right? So that makes sense to not make data products that are bigger images like this, because this is not a data product that Plato will give more than once every mission quarter, so every quarter of a year. So to do simulations, we try to understand what is the applications that we can use it for to exploit the science, and what is the limitations in terms of instrumental systematics. So for example, here, this little simulation here shows you the movement of the spacecraft, the jitter, and it shows the cosmic rays, all the stuff that we include our simulations as well. And of course, you can see that stellar contaminations, even if you do the onboard photometry, can play quite a big role here with quite a bright star that is neighboring into our favorite object, let's say. So doing simulations can help you to understand what kind of limits can you reach. And I will use that also to show a bit more. And to dive into Plato Sim, just to show you, I will show you 2 equations today, but this is just one of them. I think it's important to start from the pixel level. A lot of simulators, they go always and kind of use the assumptions that we can just say everything is Gaussian noise. And I think that's an assumption that we should try to abandon when we're doing more and more complex space missions. Especially for this project, we're really working in the faint limit of the mission. So here we cannot really avoid to really look into the devil in the pixel level details here. So if we start from a simple equation here, this is if everyone has done some observations and analyzed some data, they probably would understand some of these kind of features here, where you have some of the incoming light in a pixel ij. You have the gain of the detectors, a bias. You have some readout gain as well for the fast end electron, of front end electrons here, sorry. And you have some readout noise in the end. And of course, you convert that all to kind of like whatever bits that your detector is having. So it could be bit 16. And then if you look into detail, when we do simulations, of course, we need to split this incoming light or incident light into the pixel up into pieces. So the way that we do it in our simulator is that we say there is everything that we can get of light during the exposures, and then there is everything that happens during the readout. And of course, there's limitations to this. So the first approximation we have to sort of do is that we cannot do this in infinite small steps. So we can take a sum over some kind of number of steps we do throughout the exposures. So we call that sort of the heartbeat of Plato, because that's the smallest time scale we have to monitor to actually record some kind of physical phenomena. But of course, the smaller you make this time scale, the more elaborate your simulation becomes and the longer it takes to kind of do. And other things we also should look into is, of course, during this exposure, we have other things that we need to model. And as I said, we model more or less everything in Plato, the Plato camera. And that's include, for example, the incident light from the object that you're observing. Here we use very realistic PSFs. So PSFs that have been modeled in the lab, and we use it throughout the whole focal plane. So depending on where you are in the focal plane, we also use the correct PSF, or the point spread function that you have. We have sky background, stray light from the moon and the sun, mainly, primarily, but there's also other sources, of course. And then you have kind of some parameters that's related to, for example, the total throughput, the electron distribution effects. So you could be the flat field that we usually call in space photometry, but it's a bit different from ground-based at least. But this is just the pixel sensitivity in this sense, and then quantum efficiency of our detectors, plus cosmic rays, plus dark current, and other effects if you want to include it here. But what I think is important to remember is that we will always be limited some kind of sense in simulations when we do pixel-based data, and any kind of simulator that you always will hear about spectroscopy as well, is that at the pixel level, many of these things happen simultaneously. And that is very, very difficult to implement in a code, that when you have, for example, some electrostatic phenomena that is happening throughout the entire exposure, plus the readout, exactly when to model it is the real complexity of this problem, I'll say. Okay, so with the best effort, we have a pixel-based simulator, and we can now simulate one camera. So this is me to scale. I'm not a very tall man, but it gives you some kind of idea of a scale of one single Plato camera. But what we want to do is that we, of course, don't want to simulate one camera. We want to simulate all cameras, and we want to create light curves with our simulator as well. So let's go from this picture to all 24 cameras. And so I developed therefore like a small toolkit that we can use, employ, and launch on a computing cluster to get like light curves for every single camera almost simultaneously. And then we can then post-process them as we like, whatever you like to do, and get to a single light curve. That's the idea, and that was sort of what I needed to do for my PhD to also exploit, for example, stellar pulsations, other phenomena that is important. And all this is all available in our code here as well. So I know a lot of people already is using this for their upcoming proposals, and I will be happy to also discuss this more later on. But we have this software tool that you can freely download, install, and run your simulation as you like. The only premise right now until mission launch is that you still have to be a consortium member of Plato, but it's pretty easy. Everyone in Spain at least can get to there. Okay, so maybe I'll get a little bit of water. Okay, so let's go to the meat of the talk, which is how Plato can be observing these supermassive black hole binaries. So as I said to begin with, I'm quite motivated about this observation about spiking, observed by Hu, or at least discovered, let's say, by Hu et al. And the question is, can we both reproduce this result, and can we also use it to then look into what it will look like for Plato observing the same thing? Thinking about that we have to now work in the very faint limit, and also put the observations in the correct place. So we don't observe it from the very beginning, meaning that the instrumental systematics and the throughput, all the stuff for Plato will be highest at the beginning and then degrade over time. And we will not be observing before 2 years into the mission. So we also have like some degradation of our data quality, which actually affect the results. So that is also something we want to take into account. So, okay, so we turn into modeling these objects. And of course, to do this, we have to make some kind of mock simulations. And so we created a repository. We can model sort of like ad hoc I would say they are pretty much toy models of supermassive black hole binaries. And what you see is that essentially just the components of Spiky here. This is a replica of Spiky, where we have, for example, the red noise from the AGN variability. You have the Doppler boosting, and you have this self-lensing event that happens specific phase in time, or a specific phase or in time. Yes. Okay. And I already said that Spiky will be observed with Plato, and this is how it looks like. So you can see that we're really hitting the noise floor here when we are observing so faint. And so remember, Plato is meant to observe somewhere between 8 to 13, 14 magnitude or something like that. And we're pushing it really beyond here, going to 17 and a half, more or less. So we're really hitting close to the noise level, and not even the noise level, we're close to the digitalization limit. So where you basically have noise from how you define your bits and how you put your gain, the bias and everything. So this is quite a challenge, and therefore we needed to produce some really good simulations to do this. Okay, so Kepler versus Plato. So I'm just going to show you the result, and then we go a bit more into detail. But I think it's quite promising already to have a light curve. When we look at the official results, this is the light curve that actually came out from Smith, et al. For 2016. So it's many more data points. But of course, what the other study had to do, because they were doing some statistical methods with Bayesian inference, is that they had to downgrade their light curve. They cannot use that many data points to get a result in a human timescale. So this is the real light curve, and to compare it directly to the observation we have, then if we simulate a 24 camera light curve with Plato, is what you see on the right here. So they look fairly similar, but you can also see there is some kind of trends that we cannot really avoid. And one of the things that we are seeing is that there is long-term trends that we are not very good at correcting for, which essentially comes from that we are in a very, very high noise regime here. We have detector effects. As I mentioned, the digitalization effect is really hitting us here. And we have some data points where we just hit the noise floor, and some of the data points are above the noise floor. And essentially what this means is that you don't conserve flux. So if we use these light curves for modeling, we will always get an underestimation of, for example, the real signal, sometimes also here for the peaks. So this is important to take into account. What I do think is quite promising is though that although we have like such a challenge, we do see some of the same trends, and we might be able to kind of use it as a diagnostic in the future, at least, to say we can confirm that this result is the same as, for example, LSST or the Roman telescope that also will be coming online in a few years. Okay, the way we model these light curves, because now we were looking a little bit into the detailed modeling of these systems, is that we take the combined flux or flux light curve that is essentially these three components. Yeah, so that's what you see in the top, the flux combined from those, and we model it with some kind of like light ratio. This is just our definition here from the primary and the binary, the secondaries you see here. Sorry. And these small letters you see around here is for the quasar variability. This is the Doppler boosting, and this is for the magnification of the lensing event that you have. And remember, both of these black holes essentially could have an accretion disk. So we have to account for that both of them are basically described in the equation. But although, like, if you look at the light curve here, this eccentric binary that was discovered, or at least a candidate, is of course not having really any primary accretion disk, because we don't see it in the light curve. It should be somewhere here where we will see the lensing event. So there's probably not a lot of accretion around the primary mass black hole in this scenario here. And the way that we then model it is, of course, we take the full orbital solution of these systems and end up with a 9D parameter space. So of course we need not only the physical masses, but also we need the inclination, eccentricity, and everything related to the orbital configuration. So in the end, we have a 9D parameter space. And if we go ahead and model this system in the exact same way that was done by the study of Hu et al. Here on the left, I show you the kind of the corner plot of the posterior distributions. And it's not to show you, I'm sorry, it's a bit small here, but it's not really important to see all the different parameters. It's more like to see kind of the degeneracy that we have in this system. So we use a similar kind of modeling with Markov chain Monte Carlo simulations and sampling of this system, and we get many, many different solutions for a simple system. And so we can already say that this might be a quite degenerate problem, and that the solution that they have found could potentially be a local minimum. So yeah, highly degenerate, I'll say. Okay, so to circumvent this issue, I then also looked into, can we use other methods? Because we know if we use only Monte Carlo simulations or only Monte Carlo sampling, then we typically are underestimating some of the different distributions that we might have found in local minima. And if you go to nested sampling, which is sort of like a different kind of sampling strategy where you can take slices through the maximum likelihood posterior distributions, you typically are better at modeling these kind of like local minima and can avoid this. But in the same place, I would say doing this, we can get like beautiful fits, and this works really well. The issue is that none of these parameters have recovered to what we actually injected. And this is with you can see, this is with a light curve that was kind of modeled in the same way where we first have subtracted, or actually we have modeled out the red noise from the variability. So even a light curve that looks like this, we get a quite different signal. And if we choose different priors throughout uniform priors or anything else, we get very different results and very different local minima. So we basically have perfect fits throughout the whole parameter space for many different configurations, but we don't really get like a coherent result for just one system. So this is at least to me, a little bit of an alarm clock or alarm that we should take into account that maybe modeling with some Bayesian statistics for these systems might not be the best solution for the future. But let's see. So one thing we also did is that, well, considering that we have this red noise and we essentially don't know really what is the true underlying astrophysical model of the supermassive black hole binary, the relativistic effects, can we also model it just with, Gaussian processes? Like, so this is the damped random walk that I talked about before for the accretion flows of AGNs. And so here we are looking at the time scale. First here, tau is the time scale of this kind of damped random walk that we have. And together with the overall amplitude that we have for such a signal. So remember, these damped random walks, they have kind of like the regimes that you work in a sort of red noise regime in one part of the spectrum, and then in other part of the spectrum you have like a Gaussian noise distribution. So that's kind of what you see here. Up top of the whole signal, you have some Gaussian noise, but you also have long-term trends which comes from this damped random walk over time. And so what we see is that if we just, in the first place, here we try to model it fully with Gaussian processes. And the fit looks actually pretty well. We can model the whole thing. And this leads to questions, is this really a true supermassive black hole binary? We did then also looked at, instead of modeling the whole system all combined, we can then say, let's assume that the model that was found by Huel is true as the true underlying model. Can we then get a better fit to the data if we take like a constant model here on top of like the Gaussian processes that we're modeling with, and we get a pretty good fit as well to the data. I wouldn't say it's much better than the previous one, but if we look at the Bayesian evidence, we cannot really tell the difference, honestly. And then we can say, what if we then say we will use a wrong model as our mean level? So this is, for example, a circular binary system. And again, we see that we can almost model this to perfection as compared to the other cases. So this is quite striking, I say, that we have such a degeneracy, and this is a little bit of a danger in this scenario where we seeing with only one single spike or flare from these self-lensing events, we can tell very little actually. And of course, that's I will also probably say that this is probably the motivation for going to LSST. You have 10 years of data. Hopefully, we will see many of these bleeps continuing and be like repeating, and then we at least have some confidence that this is real. Okay, so this is a fun result, I say. Anyway, let's go back quickly to the result of this simulation that we did for spiking. And just to show you this distribution of these parameters that we have, of course, spike is a very best case scenario, right? Remember that we are observing it basically when we have the closest approach between the two black holes. So we get the highest magnification in this eccentric binary system. So this is quite a rare case of a binary configuration. And so, of course, when we're looking at other systems, we might not see such a thing. So we can take, for example, lower inclinations. The kind of the flare is vanishing a little bit, and everything here could look more like red noise, I would say. Or you can have, like, for example, lower eccentricity, and the flare again will go significantly down in this noisy data. So I would say this is, at least without any prior knowledge, and as showing you also with the Gaussian processes, this is very difficult to tell alone if this is really truly a binary system or not. And of course, we can play around and then explore the whole parameter space, which is actually the point of the future research that I'm planning to do. So let's look into that a little bit. So to begin with, what I really would like to do is that, can we expand this stage that we're on, like with having almost no supermassive black hole binaries, to have some kind of confirmation of some of them, so we can kind of build like a demographic of like how these systems, they evolve and how they look like in essentially. And to do this, I show you again this kind of like full sky plots, because what you actually see here in these two fields, again, is the northern and the southern field of Plato. But this is actually all the collected AGNs from these two fields that we have within a magnitude range up to 19 in the Gaia passband. So we have quite some, it's like more than 12,000 AGNs. But of course, observing too faint with Plato will not really be possible. So we have to discard many of these, of course, as well. So looking, how can we then make the best decisions for the future? Which one should we observe? Well, we can look at the noise level and the noise budget of Plato. But this was the study that I did in my PhD, looking at, for example, a bunch of pulsating stars. But essentially, it shows the same thing, that we want to know what is the inverted ratio of the signal to noise. This is the noise to signals ratio as a function of the magnitude of the object that we're looking at here, right? And so you can see 4 different curves of 4 different colors. And that's essentially because we have primarily all the objects observed either with 24, 18, 12, or 6 cameras, right? And when you go up here, basically have more and more noise in your light curves. But what if we go to the very bright, very faint limit, not the bright limit? If we go to the very, very faint limit, what we see is that we have sort of like a jump here down, a continuation of what we saw before. And the lines showing here is the overall expected noise level from simple calculations. So this is the orange line. You have a dotted line here, which is the background noise that we expect from the detectors and the sky. And you have the photon noise limit down here from the objects itself. And so what we kind of see is that, also what I would probably expect is that after we hit some kind of, there must be some limitations to the data, right? And we see the limitation happen somewhere around here, 17 and a half. So that was beyond the regime of spiky. And what you are seeing is that the bending off here is because we're losing signal. We don't detect anything but noise. So that's essentially what you can see. So this gives us some idea of, okay, we should probably, if we want to at least model these things, we need to have a conserved flux, right? We cannot go beyond and have some kind of flux that is missing half of the time, at least no signal for our objects. So we might not want to go all the way down here where we don't have any flux conservations. And so the ideal objects that we can sort of like look for, if we take like a simulation of, again, spiky here for a 16 magnitude case, looks much more feasible, right? But of course, the question is it really there in the data? And so we might not know if we have any such objects in our data among only so many candidates. But this is just to show that the noise level we have over time, that might be some kind of like resemblance of some signals even to the very, very, very faint limit. But again, some of these simulations here are probably a little bit too optimistic again. So you should take this with a grain of salt in the very faint limit, I'll say here. But as we go here into the regime where we're a bit more secure, I think it's pretty okay. Okay, and that was just to show you the distribution, how many targets do we have available. So you see, if we take the cut here, that's not a lot, right? So we cannot observe like thousands of these. But in the end, it doesn't really matter much, I think. I think that's not the whole purpose of this study anyway, because we might not right now be able to hunt for supermassive black holes with Plato, but we can be the monitoring survey that actually really understand what is going on with the AGNs and the accretion flows that is prohibiting us from actually observing these relativistic effects. So what I would love to do is that I would take at least a bright subsample in these two fields and then just monitor them. And we can do it very efficiently because we don't need anything but a single data point every single 10 minutes that is processed on board the spacecraft. So this is the lowest data rate that you can get, and it would be plenty enough for the analysis of these objects. So therefore, I think this is a quite unique and cool project, and also something that I will propose for the upcoming guest observer proposals. So one thing we sort of missed, I will try to also wrap up at some point here, is that in our simulations, we've also been a little bit naive, of course. I just showed you sort of I said already, a toy model of a supermassive black hole binary. But in reality, we also have more complex systems. And the reality is probably that the accretion flows that actually creates the supermassive black hole binary disks, or the mini disk of these ones, come from a circumbinary disk, right? And so how to model the complex accretion flow here is left to other people that do hydrodynamical simulations. It's not in the realm of my expertise, but I think this is important to take into account when we do photometric studies of something in the future. And another thing is that we also didn't really take into account that we live in different regimes, right? When we have the black hole binary system and they are lensing each other, we get this very characteristic lensing effect here. And we model it as a point source, but of course, if you have the binary or one of the components getting comparable to the Einstein radius, you cannot really take this assumption to that limit. So you need to start to take chromatic effects into account. And so we need to model this in the correct bandpass. For example, in the Plato bandpass, the lensing event will be much smaller because it's a much redder bandpass than these very hot accretion disks are actually showing. And I just want to give a shout out to one of our collaborators on this project as well that had a paper out here recently with kind of doing the same study that I would love to follow up with Plato, where we are looking at these kind of like hydrodynamical simulations where we have complex accretion flows, but together with that also have these self-lensing events, the Doppler boosting, all combined, but in a much more like say homogeneous way, and I would say more physical motivating way to do this. So they don't look exactly the same as you see as what we have already shown. But I think this is the way to go if we want to understand kind of the dynamical scenarios of these black holes binaries. And the way that he did it was, of course, he made some initial studies. Then what does that look if we then project it onto the cadence of the same filter, I suppose here, for LSST, and can we actually then follow them up? But of course, what I would like to do is that if we take for some of these systems a smaller cadence here, or maybe 1,000 days, that is basically what we could simulate, right? There's a bit more than 2 years. Then we can maybe get the same kind of results for Plato. And we're doing a follow-up study slowly now, starting with a big set of simulations that will probably also resolve in using this public code called binlight, which can sorry, I'm blind to my own slides. So I would like to use the software binlight because it's like a combination that uses this hydrodynamical simulations in combination with kind of these photometric signatures of binaries. So I think this is a really cool forward way to do this. And since we are really working in the faint limit, we might also look into the uses of machine learning because this is quite a unique case where we can find some signatures. Okay, so to round off here, just to give you some bullet points. Now, what can Plato offer to supermassive black hole research in general instead of just to LSST? And so I would say that Plato's is quite unique observatory to follow up supermassive black hole binary candidates to both either confirm or deconfirm them. But in the area of LSST, I think this will become quite important, that we can use a very high precision and also high cadence photometry from space to do this. And also, what I think Plato will be giving us a lot of information about, as I said, if we do kind of this follow-up study and take some data with Plato, just of some bright AGNs, what we might also get information about is this variability of the AGNs, and maybe get a deeper understanding of how can we model this, and also mitigate the effect of these kind of red noise signals or damped random walks. And as I said, we are planning to make few simulations that hopefully can uncover at least kind of the parameter space we can explore with Plato, and maybe also show a little bit of what kind of demographics that can be used in this sense with the Plato and in combination with other observatories like LSST. Okay, so that's basically it. But I just wanted to say that we have an upcoming event that I think is quite fun. And if you're interested in using Plato, I think this might be of interest to you. So therefore, I'm also presenting this. So we might not be able to explore the entire universe, but at least some part of the universe we can see with Plato to some kind of fate limit. So here in Belgium, my previous university where I studied my PhD, we have a Plato workshop, which is focusing on making proposals for the upcoming guest observer call. So you have a few days for the deadline, just to let you know. And I will be there also to give the tutorials on the simulations because that's been my of course my main bedrock of my PhD. So I know a lot of knowledge of how to run simulation for many different kind of science cases because this is also a new science case for me, for example, presenting all of this. So if you can attend, I'm around for the next 2 days, and you can of course catch me and we can talk more. So that's all for me. So thank you.
Questions?
I think. Okay, this is one. Thanks for the talk. This was really interesting. I actually have two questions that are not really related. One, going back to Spiky, and you were mentioning how you could fit several different models, and then so I mean you kind of have a little bit of a degeneracy there.
Yeah.
So how will I mean, I suppose if you're just fitting the Kepler data or just fitting the Plato data, you run into this, but combining the both of them, can you kind of remove some of these degeneracies?
Yes, that's actually a good point. Yeah, you might be able to. The issue I find probably in this kind of sense that the accuracy of the knowledge of the lensing event is so long ago now, so we don't know when that's actually going to happen. There's also an orbital precession of the system, which was recorded by Hu et al. So right now there's a plus minus half a year discrepancy, and I think that would be very difficult to take into account. But I think it's worth trying. I mean, if we get the data for Plato, I think we should for sure try to model both in the same time series and see if we can get a coherent fit. Yeah, that would be. I think it's a very good idea. Yeah, for sure.
And my second question, as somebody who's worked with both astroseismology and with these now, I was wondering if you could comment on heartbeat stars and kind of how whether or not those would be potentially sources that we could confuse with these, or kind of what differences would we, yeah.
Yeah, yeah, it's a good question. I think we need if for some of these targets, if we do the onboard photometry right, we will have a lot of contamination, and there will be a lot of stars in the field of view. Probably some of them maybe also pulsating stars and heartbeat stars. So I think the only really way to go about it is that we need to have follow observations to when we have a system we think is sort of like a candidate, we can go for really like narrowing down every single of them. But what is also good about this, I think, this project is that if we do have a candidate, we can always change the strategy maybe in the next observing round. So we can start requiring pixel data. And then we can start to play around with every single pixel and say, is this really the target we're interested in, or is it like a heartbeat star? Yeah. But I definitely think so. Like it's the same thing we had a discussion with about flaring of normal stars, like solar type stars. But the thing is that these lensing events, even for periods that are quite short, they last many days usually, which is far longer than most flaring events, right? So you can usually rule out the kind of the physical configuration from the kind of duration of these things. Yeah.
Thanks.
Yep.
Yeah, thank you also for a very nice presentation. I have worked in the past with Kepler data, and I couldn't avoid to notice that this spike light curve, it lasts for 3 years. So why is it not the whole 4 years and a half? Because
So the observation of spiky is started, I think it's almost the 12 quarters into the mission or something like that. So
Okay.
it's not the full data rate. I don't know why exactly, but I think it was later in the mission that discovered that the equators were, or some of the AGNs were actually in the field of view. And then they took advantage of this through the guest observer proposals that they have for the mission. But unfortunately, yeah, the time series is not 4 years. That would have been amazing because that would have been then directly showing either that this is a candidate, like, or it's like a real system of being a supermassive black hole binary, or it's just red noise, right? So we kind of missed the second peak, a spike. So that's what I was trying to find out with Plato, but yeah.
And was there any other effort from the ground, like CTF, to follow up on this source? Because,
Yeah.
I mean, it's like 8% in flux. I think it should be feasible from the ground, right?
Yeah. So there has been other studies as well. I think some that there is mixed results, I would say. So there's been also results from space and from ground and from radio, from X-ray, and all of it. Some of it suggests binarity and some of it doesn't. So right now it's very difficult to say. But I think the underlying message here is that when I look at the data, at least the data rate is so low, and it's extremely difficult to see sort of anything in the data, any correlation, if there would be anything. Plus, in the cases where you have these kind of like red noise signals on top of your signal, you really cannot just observe for a very short time. I think you are forced to observe continuously for a very long time to get more confidence about what you're actually looking at. So with those results that were presented, at least in the literature, I would say it's difficult to rule it out, but it's also difficult to reconfirm, I would say. But I think if I have to be honest, I think spiky. Let's see. I would never say never, but as we could model it with more or less everything, it does look like that it's just a flare of the accretion disk instead of maybe being actually a self-lensing event. But yeah, we will only have to look a bit more to see. But if you talk specific about that, the CTF, that data has been used to collect a lot of the candidates to date, but the precision of which the survey is dwarfing compared to Kepler, for example, right? And I think we really need much better precision data to actually follow up these things. So I am not sure if it will increase the chances so much, and I don't know exactly what cadence they observe this object with either. They can maximum observe it for half a year, I suppose, before it sets from ground. So, yeah.
Okay, thank you.
Are there questions at home, Tanya? Nothing? So I'll ask you one more.
Sure.
So I understand that your plan now is taking what you've learned from this one object to confirm or reject candidates. Is there potential here to also do a blind search through Plato light curves and find new ones, or it will only be working on the candidates?
No, unfortunately. So because of the science, the core science focus, and because the limited telemetry that we have, you have to ask for AGNs specifically. There's no AGNs in the catalog of the Plato mission. Everything is stars between, I don't know, F5, spectral type F5 down to K7 or something like that. So it's really not in the realm of the mission's core goals. And so therefore it's like important that we make the investigations, we show that we can actually do it with simulations, and then we can make a proposals and hopefully get some time. And I say, like, compared to maybe other kind of research, like, I don't know what will come out of it, of course. For now, it's like what I think will be a good idea is just to monitor a lot of these AGNs, the brightest ones. And as soon as we have some candidates from LSST, we can start to put them in the queue, right? And really do the short period binaries that might be very difficult to have the sampling enough from ground to actually observe them. Plato could be like a very, very good follow-up tool, I find. So there, I think it's going to be like a little bit hit and run research, because we will have to see what comes out of the LSST while we also get a better understanding of what can we actually do with Plato, if at all use it for anything. So yeah, so it's a difficult question to answer.
Okay, thanks. And thank you, everyone. He's here today and tomorrow. So if you don't find him, you can send me an email if you want to talk to him. And we are also going for lunch tomorrow. So if you want to join us, you can also send me an email. That's it. Thank you.
Thank you.